So thank you for coming. And at the last storage field day, we gave kind of an overview of our overall architecture. And what we wanted to do this time was to dive more in depth into one of the components of the system, in particular, the quality of service component. Right? So last time we discussed how the VM store basically takes I/O requests from the hypervisor over protocols like NFS or whatever those hypervisors use. And then we have a protocol manager that maps all of those operations down into per VM and per vdisk operations. So internally to our storage system, we know for each I/O request what VM or vdisk issued that I/O request. This allows us to perform performance isolation and quality of service on a per VM and per vdisk basis. And that is what is illustrated by these lines here. You see some of them are thicker than others. And we kind of sometimes informally refer to these as lanes because we can individually control the performance that a particular VM or vdisk gets. And this is very important because in most of our customer deployments, customers want to run both server class VMs and desktops on the same VM store. We don't want the kind of the throughput intensive, very heavy VMs like databases or even provisioning from VMware to be trouncing all over the latency sensitive VMs like VDI desktops, right? And to a certain extent, using SSD does help in the sense that it increases the number of IOPS that's available. So it makes it less likely that the actual disk spindles are bottlenecks. But there are many other resources in the system other than just SSD, right? There's networking, there's memory, there's NVRAM, there's disk IOPS, all of these type of things. And any one of those, and even the flash IOPS can be a bottleneck depending on the workload. So it's still very important to be able to provide quality of service basically on an end-to-end basis, because what flash does is it moves a lot of the bottlenecks from disk to other components in the system, like your networking hosts, other things, and you still have to deal with that. The other thing is that with flash, it enables us to build very, very dense storage systems. I mean, today, we have storage systems that can run hundreds, even 1,000 VMs very efficiently on a single 3U appliance. In a few years, that's going to be probably 10,000, even tens of thousands of VMs on a single appliance. When you get to those levels of density, you're going to be running a very wide collection of workloads on the same box. And if you do nothing about quality of service, some of those VMs just are not going to get the performance, the latency, or throughput that they need in order to perform their work. And furthermore, depending on the applications, users will want to express their preference as to whether certain VMs should get higher levels of IOPS or other kind of performance resources. Right? So this is why it's important. And now what we're going to do is kind of dive into what have we actually done in order to provide this per VM level of quality of service. So Mark is going to start off the whiteboarding here.
Sure. So as Ed mentioned, VMs are really the right level of doing this. And one of the things that validates this is if you look at the VMware ESX, there's actually, with storage I/O control, a queue per VM. Unfortunately, once you dump it over the storage array, most storage arrays throw that all out the window, and you've entirely lost which VM contributed which read or write. So there's a potential bottleneck within the network layer itself, the networking stack on the controller. You're sharing buffer resources, you're sharing kernel resources. The CPU itself can be the bottleneck. Particularly in all modern file systems, you're actually doing quite a lot of work to read and write. In our system, you're uncompressing the data, you're doing metadata lookups. All that can actually become the bottleneck, and you may have to prioritize at that level. In our system, that's not usually the bottleneck, but we're trying to illustrate, there are a variety of places. One that's a little non-standard is, memory can be the bottleneck, particularly because that's where metadata gets cached. Even with flash, you don't want to be taking multiple flash misses, multiple flash reads to provide one data read. You'd like one read from the customer to be one read to flash, not multiple reads to flash. And so on a per VM basis, you would like no one VM to dominate your cache. You'd like fairness and consistent behavior for a variety of workloads.
Yes. And particularly, even though flash is fast, I mean, every I/O to flash today takes on the order of maybe 200 microseconds or something. So there's a big difference between making one flash access and then 3 sequential accesses because you have to do 2 more metadata lookups.
Flash is only really fast by comparison to disk.
Right.
Yeah. And in our system, you know, we have both flash itself, and there's a queue on entrance to this of who gets to read first. As the load goes up, that queue can grow in length, and it's important to be fair and provide performance isolation at the flash layer. You know, a lot fewer requests go to disk, but there's potential for the same queuing delay there. And in particular, you would not like 1 or 2 bad VMs that are experiencing a lot of cache misses because their behavior has radically changed or they're accessing old data to interrupt systems that are still being well behaved.
And of course, another type of memory resource would be NVRAM. Most systems have a limited amount of NVRAM to buffer write. And so if you've got one VM that's writing a ton of data, they could easily hold up like desktop or something, which is just trying to write a little bit of data and get back to what it's doing. So,
yes. And finally, you know, once you've got the data or have done a write and got the response, you have to go back through the networking stack
send the reply.
To send the reply back to ESX. And this is an area where we've done the most work, is we actually have a per VM queues using a byte level fair share algorithm to ensure that no one VM dominates. We actually saw this in a lot of people doing provisioning workloads where writes were being starved by reads. You do a lot of reads, particularly when you're provisioning, a lot of those reads are 0 reads from a thin provisioned disk, which we can spit out at megabytes and megabytes per second.
Right.
And meanwhile, your write response is this little packet somewhere stuck somewhere back in the queue here behind all these multi-kilobyte reads.
Right.
And so even though we were writing the data to flash very quickly into NVRAM, and NVRAM wasn't full, because there was the shared contention on the network resources getting back to ESX, we actually saw a big improvement by making that fairly shared among the VMs using it.
Yeah. So things like provisioning and storage vMotion are actually very I/O-intensive operations, which can have a big effect on the latency of other VMs running on particularly the same host, but also sharing the same store system. In fact, Tintri does, in our UI, we provide a breakdown of end-to-end latency based on where the latency is spent. Is it in the host? Is it in the network? Is it on our store system? And what we found is that if you have provisioning or storage vMotion running, the host latency can oftentimes increase dramatically, sometimes in the orders of tens of milliseconds.
Yeah. So one of the things, because we are a tiering system, is not only the queues for writing flash, but how do you divide up flash? How much of this flash should be given to a particular VM?
Right, or the NVRAM, for example.
And the same applies to NVRAM, and I mentioned memory as well. Yeah. All these resources ultimately need to be fairly shared to ensure there's not a bottleneck caused by any one VM.
Yeah. And you can see that there's here 2 main classes of resources. There's kind of the dynamic resources like the flash or networks where requests can be switched back and forth very quickly. And then there are some static resources like NVRAM, memory, and flash, which take time to be allocated, right? So it requires different kinds of allocation decisions. But the point is that depending on the workload, the environment, the mix of VMs, any one of these resources could be a bottleneck. So unless you are controlling the queuing allocation of each one of these resources, you cannot guarantee end-to-end quality of service, because it's kind of like a data highway, right? You have the data flowing through the system, whether it's a read or write request, it's going through the various resources, the various queues, and it doesn't matter if you fairly allocate, resources here and there. If they all block here, then everyone's going to end up in a big traffic jam right here. Right? So this is not a simple problem that you could just address at any single level in the system. VMware certainly does their share of the work by controlling which queues, which VMs are allowed to queue more requests into the system. But once it gets into the system, you also need quality of service mechanisms at this level as well.
And as Ed mentioned, the right level is really the virtual machine. The user can tell us on a virtual machine, this is important, versus this is just some rogue VM operating in an unusual fashion.
Right. So Mark, maybe we could quickly run through maybe a sample read request. In particular, maybe read requests from two VMs. One is the big read request from a database, and another one might be small read requests from a virtual disk, and see how it interacts through the system. Yeah. Do you want
sure.
two colors? Or? Or I could draw one and you can draw
why don't you draw the small
okay,
request?
Let me first draw the evil database VM, which is soaking up all the resources. So say you have a database and it's doing a big database scan. It's doing these huge reads for maybe even megabytes of request data, and it's queuing a huge number of those requests into the system, right? So what you end up with is streaming large amounts of requests over the network. It's going to, those requests have to, are going to use CPU resources. They eventually have to be queued on the flash. So you have these large requests. Here's one request, here's another request, and here's another request. There's an endless queue of requests because it's queuing so much data on the system. It's going to be queued and serviced by the flash device. And then all of those, the data that's read has to be now sent back out over the network. So you've got these requests, again, queued, kind of saturating these network interfaces. Now, the network interface today, we have 10 gig, but 10 gig is not that much bandwidth. It's a gigabyte per second, right? A single Tintri VM store can easily saturate a 10 gig network. So now, what happens now if you have a bunch of small VDI desktops that are issuing lots of little requests? They don't use up a lot of bandwidth, but they're very latency sensitive. What happens?
Yeah, so the request size is the same, whether you're doing a big read or a small read, obviously.
You mean the frame size, but the actual request size.
Sorry, the
packet
size,
right, packet size
coming in is obviously independent of the size of the read you're doing.
Right.
But the amount of CPU needed to uncompress a big chunk of data is obviously different than a small packet. The amount of metadata touched by something scanning over its entire database could easily thrash the page cache as we touch all the pages in a very large B tree, whereas the desktop is going to be more or less keeping to its working set, and we want to preserve its access there. As Ed said, Flash, the database could be very parallelized and have a lot of requests outstanding in Flash compared to an interactive VDI environment where there may be only one or two requests that need to happen before the user sees something. So again, we may have a very big queue for the database workload and only a couple items queued for the Flash, for the VDI instance.
And if you didn't do anything special, what might happen is we service a big database request, service one little request for VDI, and then a big database request, one little request for, and the result of that would be terrible latency for all of these VDI desktops, because you've got 1,000 VDI desktops, each issuing only maybe 10 IOPS, but in aggregate, there's quite a significant number of IOPS, and you're only servicing one little, desktop request for this huge, database request, right?
And then, as we mentioned, when they go back out, now the read size does make a difference, and something that is the virtual desktop is swapping or it's accessing data randomly may only need a 4 kilobyte response, where the database is very optimized at disk traffic, and as a result, it's doing a large maximum size 64 or 32 kilobyte request. And again, more of them in the queue.
Yeah. So what we found is that in our own measurements and in our labs and actually seeing the system in operation, before we had these mechanisms, if you had a mixture of the databases and desktops, the databases would get almost all of the throughput, and the desktop latencies would really suffer, right? And once we put in these mechanisms, now if you do provisioning, storage, vMotion, those things, it doesn't really affect the latency of the databases.
Well, one other thing we noticed due to a problem in our lab infrastructure, we didn't actually realize how overcommitted in memory we were. People would show up on Monday morning, log into their virtual desktops and say, why is this so slow? I'm running on a flash device. Well, it turned out not to be I/O to the virtual disk. It turned out to be I/O to the VMware swap file. And VMware swapping is very, very slow. The whole VM comes to a halt before you get that I/O back to it. So what we actually put into the VM store is a feature that prefetches VMware swap disks, that we've tuned prefetch to when an access comes to a VMware swap disk, prioritize that, get that into flash or even DRAM so that we can respond to it very quickly and swap the Monday morning user back in. And we really succeeded in making the user performance better, and then we ruined our test bed by actually provisioning enough memory for the number of VMs we were using.
That's what happens if you try to mix test and production.
Yeah. So really one of the big challenges in designing all of this is there are many quality of service mechanisms that are available, but there's few that are actually used on a regular basis because they're too complicated for people to understand what's happening in the system and then what knobs to tune, right? So what we're trying to aim for is provide a default level of isolation and fairness, which is good enough for 90% of the applications, and then to give users the opportunity to express preferences in terms of, this VM should get more resources or whatever. But you cannot auto-tune the system too fast. It's like, if you ever tried playing a video game from the 70s on a 2010 PC, like you hit one key and because of the internal timing loops, it goes and it's game over, right? So if you tune too quickly, the user doesn't get a chance to provide feedback into the system. So part of this isolation mechanism is to ensure that some of these resource allocation decisions, especially if you are under heavy resource contention, change relatively slowly so that the user actually notices, well, this VM is now starting to accumulate a lot of performance resources. Do I want it to get those resources, or is this some kind of runaway berserker VM? That's a term we've invented, berserker VM. I should slap the hand of the guy who wrote this, and before he fixes it, I should tune down the resources it gets, right? So those are some very interesting user design issues. And I think one of the big challenges in designing effective quality of service systems is actually showing people how it's affecting the performance of their VMs. And that's one of the big things we are going to focus on now is visualizing contention in the system and then giving them the right mechanisms for affecting how the system allocates resources. Because they simply cannot set shares, limits, and quotas on every single VM in the system. That's just not going to work. And even if they would manage to do it one day, a month or two later, their allocation would be wrong because the resource needs of their system would have changed. Right?
So in the current release, is this all, do we have tunable QoS and
Yep.
IOPS and latency limits or goals
Right.
on a per VM basis?
So we
or
have,
are you basically working on fairness at
Right.
this point?
So what we have are internal mechanisms for enforcing it, and then the user level mechanism we've exposed right now is pinning. In the future, we will expose more mechanisms. We considered many more complex knobs, but we just couldn't find a way to make them effectively usable without also providing a good visualization of how the system creates contention. So what we are going to focus on now is the visualization mechanism so that we can provide better tuning knobs for users.
Yeah, so they're
because storage QoS is really the next thing.
Right.
That you guys and SolidFire and now I forget if it's NextGen or T-Child, but one of those two are all talking about, as we start running Flash and multi-tenant and
Absolutely.
getting more and more clients accessing the same storage system, that managing QoS is going to be the next major problem.
Right. Imagine a 4U storage appliance, 10,000 VMs. What's going to happen is like, an analogy I sometimes like to use is that in the world today, there's enough food for everyone. It's just not getting to everyone. So same type of problems will occur here.
Well, I lived in New York for a long time where I had to worry about noisy neighbors.
Right.
Now I live in New Mexico.
You have different
and
issues.
Noisy neighbors are 2 miles away, it doesn't matter.
Yeah. So that's the basic information we wanted to provide for you today. Any more questions? Okay, thank you.
Thank you.
Well, I did have a question.
Robin?
Okay.
Robin?
And the whole issue of the per VM management, I mean, I think that's one of the really cool things that you guys do. And yet I've heard that that's the direction that VMware is going in. So maybe this is an interesting question. I mean, so is the per VM management model really going to be a continuing competitive differentiator for you guys, or is this something that everybody's going to have in another year or two?
Right. So we really like the direction people are going of acknowledging that there is a problem there, that VM awareness is the right thing. We'll be working with VMware on vVols, but what we're seeing is a lot of the things that they're saying, you need to support X, Y, and Z, we say no problem, already doing that. And I think we'll be ahead of the game on both implementing the standard protocols and providing services in advance of that for a while to come, because we've got a good base of technology to work on.
1,000 customers across which you can see the second and third order problems, and everybody else is just going, oh, well, now we solved the first order problems, and they haven't even seen the second and third order
Absolutely.
ones yet.
And I think you have to very clearly distinguish between the vVols API as defined by VMware, and that API is implemented by various storage vendors. Just like today, and I mean, NFS is an standard API. There are many different vendors that implement NFS. There are big differences in the quality of those implementations.
No, I never noticed.
It's a standard. It's all the same.
That Microsoft Services for Unix, it runs great.
But what we found with VAAI, our experience with VAAI, and you could think of that as a precursor for vVol-like functionality, is that a lot of people implement VAAI, and what we found is that if you have a really good implementation of VAAI, like we have cloning implementation, it actually allows our customers and VMware's customers to take better advantage of our functionality. So for example, because we do cloning through VAAI, not only can you right-click and clone a VM from vCenter, but any clones you create from View or View Cloud Director automatically also use Tintri clones. So these interfaces actually allow our customers to better leverage the functionality we have. So it's been a huge positive for us. And we are a design partner with VMware for vVols, so we will be working actively on that as well. Okay, thank you.
Any other questions?
Somebody else has that question.
Hyper-V support? It's been...
Or any other hypervisor.
We've started looking at Hyper-V. I can't comment on when we'll commit to doing that, but
you will commit to doing it, right?
Yes. Our goal is not to be tied to VMware forever. Sorry, but to be multi-hypervisor. The technologies we've built will work in other hypervisor environments as well.
And the last time we were here, that slide said SMP. Actually, I think it said SIPs, which would have been wrong.
This is the simplified marketing version, and they have gone too
It does say
far.
hypervisor.
Yeah, you're here, you have a plural, so that what is the...
Eventually there will be multi-hypervisor. Yeah, I mean, we're not, just like you said, we just haven't committed yet to it. Thanks, Mark, and thanks, Ed. Appreciate that. That was a deep dive. Thank you.